Let me share my screen with you. Oh, give me 1 moment. 1 moment before I start sharing. I have to do something else. I'm sorry, I was talking and my mic was on mute. So last week we talk about hypothesis testing for population proportion, and the week before we did mention confidence interval, stuff like that. So make sure you review these notes so don't get confused to you whenever taking the exam. Again, you're allowed to use a little cheat sheet on the exam. Okay. So today we're gonna we're gonna be talking about kind of the same thing, but this time we'll be talking about population mean compared to population proportion. Okay. So let me just show it to you. Again, the week before, we're focusing on sample proportion. We talk about the p hat. We're trying to define p. So as you can see, we assume that this parameter is unknown. We try to define p. That's what we're doing. Now, this week, we're going to be talking about simple mean, this guy. We're going to have X bar. We will try to identify mu. Again, as I said earlier, the X bar trying to define mu, and then p hat trying to define p. As you can, if you can go further on that, you can say letter S for standard deviation, trying to define sigma. Okay. So this is this two right there. Or I can say S squared trying to define sigma square. All right. And we spoke about, again, we already spoke about this guy. Now we need to talk about this one. Okay. And so on. Does anybody have any question? Okay, so I just want to make sure that you don't confuse the concepts. We're gonna be doing the exact same thing, just like before. We're gonna do confidence interval. We're gonna do hypothesis just for the mean. But before I do the confidence interval or anything else, I need to introduce to you the mean I look like, the simple mean. Okay, how does it look like? So we're gonna need two things all the time. You're gonna add the mean and standard deviation if this equation has a numerical variable. So if this is the mean here, mean and standard deviation. Okay. If you're doing proportion, usually it's gonna be yes or no. Okay, but we already spoke about proportion. So in this concept, we're going to be talking about this guy right here. Okay. Again, for this guy, we're going to need, okay, let's keep working. The confidence level hypothesis test always refer to population on the sample. Okay, that's just something we need to remember. Whatever study we're going to be doing, if there is confidence interval, we're going to try to understand the population, okay, but not the sample. Okay, that's why whenever we have that interval, whenever doing for proportion, we try to know where P is belong. For example, if you're doing proportion, so for confidence interval, it'll be something like this. It's going to be P hat minus E less than P less than P hat plus P plus E. As you can see, P is the unknown. So P is in that interval. P is in the range. For mean, it goes like this. It's gonna give you X bar minus E less than mu less than X bar plus E. As you can see, they follow the same pattern. The only difference between the two, the E are not the same. Okay? The it's not the same. I always explain to you how to find the E in the previous classes. But now this time we're gonna try to focus what is this E is for the mean. Okay, we're gonna try to understand this one for the mean. This one over there for the population proportion, we spoke about it before. You know how to get that E. So we talk about it. So if you did notes, we talked about this one before. That's proportion. So again, we try to define the population proportion or the population mean, not the sample proportion, not the sample mean. Again, we'll try to define the population proportion or population mean. Let's put population. That's what I'm trying to understand, not the sample. We're gonna use the sample to understand the population. That's instead of doing a study on every single people in the population, then we take a small sample, you study some sample to get an idea of the population. And this is what we did for the population proportion. We're gonna be doing the exact same concept for the population mean, okay? So let's keep walking. Okay, this one say if the mean is accurate, then the average of all sample means will equal the population mean. As you can see, the same concept we talked before for the population proportion. So we say that you can use the P hat for P, you got the same idea. So you say if the sample mean is accurate, if it's accurate, then the average of all sample mean will equal the population mean, okay? So that's in it. So if a sample random sampling is used, the sample mean is accurate, also called unbiased. That means make sure that you think is random. Like that is the keyword here. I know it says sample too, but I need to be random. Okay, that's mean anybody and any sample in the population are the same chance to be selected. That's mean if you go and select your sample, you don't select everybody that you know will be agreeing with you. You're gonna select people, anybody. Suppose I'm trying to do something about Democrats. I don't select people from my family to do the study because if they know that I'm a Democrat or a Republican, they're gonna tend this gonna alter their judgment. So therefore, it has to be completely random. It's just simple random, and don't mess it up. Then that will be accurate. And then whenever it's accurate, we're gonna say this is unbiased. Okay, not biased and non-biased. So so these are, so they don't about this little part here. So we talk about this one. I think we talk about other sampling technique can be looked. So we talk about non-parametric, but not about this one right now. Okay. So this is for reading. These are the precision of a sample mean describe how much variability there is from one sample mean to the next. That's just the things that we want to understand. Okay. But I'm gonna show you a quick picture soon. If the population standard deviation is small, if the population standard deviation is small, the sample mean will have more precision. If it's a small, if the standard deviation is small, then you have more precision. So this is something that you need to remember. Okay. If your standard deviation is small, then you have more precision. Okay. If the sample size is large, then also you can have more precision. This is the sample size will be n. If n is large, then you're gonna have more precision. If the standard deviation is small, let's put sigma, for example, is very small, then you got more precision. Okay. So this is the definition of precision right here of the sample mean. How much variability there is from one sample mean to the next. Okay, now let's look at the picture quickly. Here we have a picture of a sample size of n. As you can see, is close to the center or close to the mean. Then if I is on a bigger sample size at 500, as you can see, it's got the closest to the center. And then you get another one, 1,000. It's like the lines coinciding exactly with the center. As you can see, the closer, the more sample you choose, the bigger your sample, the more precise you are. Okay, the more precise you are. The bigger sample, the more precise it's gonna be. So that's me. If you're doing a study, you have a huge data, and it's gonna be more precise. Okay. Also, if I ask you to do a study, you only ask 2 people or 3 people about something, it's not gonna be it's not gonna be a good thing. Okay, that study will be just biased. But if you use a good sample size, then that should be fine. Usually, in this case, a good sample size usually is n is equal to 30. Minimum 30 is a good sample size. But beyond that, I mean, before that, then you have to do some other procedure. I'll be talking about that down today. Okay. So you can see, as the sample size increase, you got better precision, and the accuracy does not change. Okay. Any questions so far? Okay. And now I need to introduce you to just like the class we did before. We spoke about something called a standard error. Whenever you're doing the population proportion, we spoke about standard error before we talk about the margin of error. If you don't remember the term I'm talking about, so make sure that you try to review the notes. So I'm going to be doing the same thing for sample. For another sample, this is what I call a standard error. The standard error is the standard deviation of the sample distribution. So we got mu x is going to be mu x is equal to mu. And then standard x is equal to sigma over square root of n. Okay. This is the standard error. Okay. So we got sigma over square root of n. And then you got mu x right here, and then you got sigma x. Okay, so make sure you pay attention to this one. I don't know if you remember for the class before, but look at the class before, whenever we did it for the population proportion. Okay. So make people give it a good look before I keep going. Does anybody have any question about it? Before I keep going. If I can remind you a little bit on before for the standard error, the mu we had mu p hat, something like that. This was equal to p, something like this. And if you remember, that was for a proportion. And also we have sigma p hat. It was equal to what's the formula again? You guys try to remember that? I think it was just the square root of p 1 minus p over n. This is how we had for previously. Now we're doing the mean. Okay? We're doing the mean. That was for proportion. That was before. So we're done with that. So I'll tell you this kind of the same thing we're going to be doing. But we're going to do this time for the proportion. Done. Okay? So now we're doing this one. Okay, just double checking. I just want to remind that it's important. Now let's talk a bit more about the population, that information. Okay, so let's go back down here. Okay, this is the standard error. Okay. As you can see, the smaller it is, the standard is smaller for large sample. For example, if you put a factor of 4, then it will be decreased by 2. If you do factor of 100, it's going to be decreased by 10. Okay, that's mean the larger n, as is n is large, if n is very large, then sigma x bar will be very small. Okay. If n is very large, then sigma will be very small. Oopsie. Okay. Just want to put some parentheses right here. And the honor is very small. I will give an example to just give you an idea, okay? But before, let's do something. Let's do that. This, for example, just want to say the mean cost per item at the grocery store is $2.75. That's the mean score. The standard deviation is $1.26. The shopper randomly put 36 items in a cart. The first question would be, is $2.75 a statistics or parameter? If I remind you before, and just remind you quickly, what do you call parameter? Parameter would be mu and sigma. That's been for population. Statistics will be X bar and then S for sample. This is for sample, and this is going to be for population. Okay, so this is my question to you. Do you think it's gonna be, do you think X 275 would be X bar or a mu? That's why I say parameter or statistics. Do you think it's gonna be an X bar or mu? This one say the mean cost per item at the grocery store is $2.75, and standard deviation is $1.26. A shopper randomly put 36 items in a cart. Is $2.75 a parameter of statistics? Okay, thank you for the answer. This is what happened. For statistics, For statistics, if you have to do statistics, this is what happened. You need to deduct it from the, if suppose I say out of 36, I would say out, if I did say out of 36, then you calculate something, right? Here it didn't say that. This is a general idea. It's on general, this is the price. We didn't calculate it. It didn't say that from 36 items, this is the mean. It didn't say that. So therefore, we need to treat this one as a parameter because that's a general idea. Okay? So that's a general, you're gonna say this is called a parameter. If I did say, I select 36 items, out of the 36, when I select 36 items, I did the average myself with my statistics, you find them. Parameter is given to you. And then I'll calculate the mean and I find this, then that'll be statistics. Statistics, you've calculated them, parameter, they are given to you. That's something you cannot find. You don't even know how to get it. I didn't know how to get the $2.75. I have no clue. They just say it. I didn't know how they got the $1.26. They just say it. But if I knew the process and it said out of the 36 sample, we find the average of 36 and find this number, then that'll be a statistics. Then therefore this is a parameter. Okay. So this one says to predict the average cost per item and a shopper's cart. I know this question look weird, but what do you think on average the cost of the item will be? On average, what will be the cost of the item? You say predict the average. Oh, there you go. That's it. 275. Thank you very much. 275 is the cost, okay, on average. Because it did say this is the mean. All right, up there it said this is the mean. Okay, what is it? Is they say this is the mean. So that's when average is the same thing as mean. Okay. Now we need to find the standard error. So you got 36 items. Oopsie, I gave it too fast. So to get the 36 items, this is what happened. As you can see, you got $1.26. The average for 36 items is going to be 0.21. Okay. But suppose that guy only bought one item, just double check it. Suppose he bought only one item. Okay, suppose he bought only one item. Why with X, this is what happened. X, sigma X bar with something like this. 1.26 over square root of 1. And that's just going to give you 1.26. As you can see, for smaller sample size, you have a bigger, the bigger your sample size, the smaller your standard error. As you can see, for 36, you have 0.21. Just for one, you have 126. And if I put 2, we have put 4, then that'll be twice that number, etc. So the larger your sample size, then the more accurate you can have for the standard deviation. If it was here, he went and took like 45 items, then that number will be smaller again. Okay. Okay, so parameter, again, parameters are for population. Parameters are for population. And then the one that describe parameters are called the mean, mu, and the standard deviation, sigma. Okay. Parameters are for population. And then the element that characterized by parameter is going to be the mean, mu, and the standard deviation, sigma. For statistics, okay, is for sample. The element that characterize the statistic are called the mean X bar and standard deviation S. Okay. On the other side, the parameter, the statistic try to define the parameter. Okay, we use statistics to try to define the parameter. So the statistics, we can find them. Parameter, which is the one that we're trying to understand. To get element for the parameter, we'll probably have to do a census. Okay. I don't know if I answer a question, Jacob. Okay. And also there was a class we did on that as well. You can just go review it if it's hard to understand anyway when I was trying to explain to you right now because the short of time, something like that. Okay. Let's see. Let's do one more example on that. For example, suppose you have a standard deviation of sigma is equal to 12,000. Okay. And the mean is 47. This is the mean mu. It's 47,000. This is gonna be considered population because I don't even know how they get the 47,000 or 12,000. Okay, because this is for example of the city. If I have to do it myself, I'll probably say like a few people, like 30 people minimum, then find myself that will become a statistic. But right now, they do it for the city. I cannot do it for the city myself because that's gonna be very time consuming and a lot of thing. And then I'm just a regular person. Nobody's gonna be on time anyway. So it's gonna be hard to do for the entire population. Maybe the city can do that. Okay. Probably the city can do it or the state can do it. Okay. But me, I cannot do it. I'm not be able to cut this number accurately, but I can do it for a small sample. Okay. This one says to find the standard error for the following sample size. Suppose you select one person. So the sample size with the standard error will be just 12,000. This is what happened. You're gonna have what is it again? You're gonna have standard error for X bar is equal to 12,000 over the square root of 1. Okay, that's gonna give you the same number. Suppose you put n is equal to 4, it gives you 6,000. Again, that will be sigma X bar is equal to 12,000 over the square root of 4. Okay, and that's going to give you 2, and that's going to be 12,000 over 2. And that's what I got number. 12,000 over 1, that'll give you the same number. And then you got to 16, and then you got 3,000, etc. As you can see, the standard error keep going down as your number increase. It's for 100, 1,200. Okay, that's the standard error. So the number is getting smaller is because the bigger your sample size, the more accurate your study is gonna be. The bigger your sample size, the more accurate the study is gonna be. Okay. That's what I want to put out to you right now. So the bigger sample size, the more accurate the sample size is gonna be. So we need large sample, not small sample. Okay. So right now I'm gonna try to go a bit more technical. And this is just an introduction of the standard error. It's just to be a little bit more technical here by talking about the central limit theorem. I think we spoke about this one for the proportion before. Now we're gonna do it for the mean. Quick definitions. Yeah, it's against random. That's the keyword. Okay. Then you're gonna assume the population to be normal. Normal means that you follow that bell shape. That's very important. Sample size is large. We assume n to be large. For the proportion, we say that NP must be greater than 10. That means it is large. But here, it has to be at most 30, but no about it now. So I will talk about it later on today. Population size is at least 10 times bigger than the sample size. Okay, that's one key. I'm sorry. Okay, so sample size is large. Okay, let me just put it down here. I'm going to talk about the other one. Usually, N must be greater than 30. Okay, greater than 30 is going to be something like that. We're going to be talking about that one later on. That's mean this is large. Whenever you use pseudo for proportion, this is for the mean. You need to do NP greater than 10. That means this is large. Okay. So if it's greater than 10, that's this is large. But now we're gonna say now it's gonna greater than 30. Okay. That's for earlier, that was for proportion. Don't remember, don't confuse proportion and mean. But this is for proportion. That's what we did before. Now we're doing for mean. Okay, mean, simple mean. Okay. Now we're gonna be talking about that 30 thing I was talking to you earlier.
Can you go pause a little bit? I just was writing it down, and I just need one part, the little corner part, to write down.
Okay, right here.
I'm done.
Okay.
Thank you.
All right then. So this one says if the population distribution is not too far from normal, then the sample size can be small. So if you was, even though it is small, but if it's normal, we still can use the formula. As long as it is normal. That's one thing you need to remember. If it's normal, then it should be fine. Okay, even the sample size is small. I mean, even though you have a small sample size, then it's fine, you can use normal. Now, this is another difference what I just told you earlier. This one said to be N25. This is kind of really, we like to use 30. Some books use 30, but your book want to say 25. So for now, we're gonna have to say 25, but I prefer to say 30 because it's the most accurate one. But your book would like to use the term 25 instead of 30. Okay, because this is like the minimum, the very minimum. Okay, that's a very minimum. This is one say for most population distribution, N is equal to 25 or higher gives sufficient accuracy. Usually N is equal to 30 is mostly the one that we usually use, most book use. But the book that we're using right now probably did so much study and say that that's why I say for most. For most, that's the keyword, most, then 25 should be fine. So for now, we can use 25. Okay, but in general, this one I was talking about in general, right here, I said 30, that's gonna be in general. Okay, so that'll be, let's put it down here in general. Okay, it's gonna be that one. But for most population distribution, something greater than 25 should give you enough for it to be enough satisfaction. Okay. So if your population distribution is not normal, then you must have a large sample. So if it's large, then you can use the data. Okay. So if it's large, and then if it's not normal, then you can use the data, but it has to be very large. Okay. Even though it's not normal. I don't know if I made myself clear enough. Then let me try to summarize what I say. Suppose N is large, and then not normal. When I mean by N is large, the basic one will be N greater than equal to 25 for almost, okay? Not no more, then you can, that's okay. Okay, also if n is small, let's put large right here. N is small, maybe n is less than 25. That'll be small. And this one has to be normal. That'll be okay. Okay to use any formula I'm gonna be doing. When it is not okay, I'm gonna say not okay. You say okay, I had to spell it okay. When it's not okay, n is small, and then not normal. So if any one is not okay, and any small and the population, I mean the distribution is not normal, then that's gonna be a problem. Okay, so it's not okay. In this case, you need to do something called non-parametric. Non-parametric. So what you do in your school, in your class right now, we use parametric. This is for parametric. So how about my parametric? Everything that is there are for parametric. The other one will be non-parametric. So we used to subtract some of the type of formulas. They're gonna be not going to do in any class, but in your class, I'll be using parametric only. So therefore, either and if n is normal, then it's fine. Okay, we can use whenever it's n is normal, it's gonna be fine. Whenever n is normal, it's gonna be fine. I forgot to put it on another case. It is also okay when n is large and then normal. And this is okay as well. Okay, three okay. You got three okays, like 1, 2, and then 3, and 1 bad. Okay. Okay, let's just put it out all the way there. Oh man, that's not bad arrow. Okay, so let's go all the way here. Okay. All right. So if it's large and normal, this is the ideal one. This is the ideal one. That's what I like to have. There's no problem with that. It's a large sample and then this normal. And also it can be a large sample, but no normal, I'm fine with it. It also can be a small sample, but if it's normal, I'm okay too. The only time it's gonna be a problem if it's small and not normal. Okay, so previously, whenever you're doing the proportion, you only have to do NP greater than 10. That's all. If one of them less than 10, that's a problem. But now we have to be a little bit more careful. Okay. So now let me introduce you to the exact term of the central limit theorem. I know this one is not new to you. I mean, this is new to you. This is what we do. This is for the mean. Okay. If I can remind you for the proportion, this is what we did for proportion again. Remember proportion. I'm trying to do that for each time so you can remember. So you kind of the same thing. For the proportion, we did n was n. There was p hat, then comma, Then be square root of p hat 1 minus p hat over n. That was what we did for proportion. Okay, that was previously. This one, we're done with it. Okay, we're doing that one. Now we're doing for the mean. We're doing for the mean right now. Okay, I got my pen back. This is done. Okay, which is like I'm teaching the same class over again, but with different tools. Okay, with different tools. And then the general term that we use is always going to be n, like this. In general, that's going to give you mu, and then sigma. Sigma. Okay, that's a general term. And then for this one here, will be n mu x bar sigma x bar. That's a general term for the mean. For the proportion, we have n mu p hat sigma p hat. Okay, just so we're right that this one is done. Now, what I'm going to show you to you now is just a couple picture, but don't let you fool about it. Is that something? This is a picture of something that is screwed to the right. As you can see, whenever it's screwed to the right, that's when you got the right tail. And this one is normal, so you got the bell shape here. Okay, you got the bell shape right here, the bell shape. So this is the ideal situation for us to write, to work the study. We're gonna also approximation normal. We have to be normal. That's why you have normal. That's so just to remind you what normal look like. Yeah, you must have that bell shape. You can have a school, you can have anything else, okay? But it needs to be normal. Normal. The term I'm going to be talking about now is just in case you find them in the exam, but you can just, if you're not, you just have to write them down somewhere. But if not, I mean, if you don't find them in the exam or the review, just don't worry about them, okay? Just terms for you to understand. The first one say, if you have a population distribution that is uniform, then your segment distribution will be a mount shape. If you have a population distribution binomial, your segment distribution will be unimodal. Okay. If you have a population that is skewed to the left, there will be segment distribution will be symmetric. That's just term that you need just to remember. Okay. If it's not symmetric, it must be segment distribution symmetric. So the last two kind of the same thing, whether it's skewed to the left or whether it's not symmetric. You want symmetric idea. Okay, these are just terms that you can use just in case you see something like that. Yeah, and then you see something like that, then you just use this little page and write them down. But beside that, you can just be careless about those terms. I don't use those terms all the time when I'm teaching. So, but I mean, I don't put them together, but I use the term population distribution all the time, sampling distribution, stuff like that. And then, but I'd use the term, but compute them like that. I mean, we talked about it before. Like here, that's going to be, for example, that's going to be for the mean mu. You see that? This is mu for population. And that'll be X bar for sampling. You understand? Something like that. But I don't put them all the time like that all the time. So it's good to know. You can just write it down. And then if you're not, I mean, after that, after school is over, just throw it away. Okay? Just in case you have a question like that on the exam. Okay? They say, oh, interpolation is distribution is binomial. A, is it semi-distribution unimodal? B, semi-distribution symmetry. C, then you know what to select. That's good to know. But I don't really use the terms because I already told you X bar is trying to express the mu, but this is too much time, okay? That's on this side. Now, one thing I want to point out to you, like I know I would something that's a P of X equal to X bar is less than 72. Just want to point out something to you. Whenever we used to do problems before, I think I remember whenever you have to find the z-score something, suppose you give you let's see, you give you a mean mu and they give you standard deviation, and I ask you to find the z-score for it. Then you do, and then for any x value, you do x minus mu over 6. I don't know if you remember these things. I hope so, okay? Something like that. But usually we usually put P of X something, P of X less than some number. One moment. We usually put that. Let me just look at my thing. P of X less than, or P of X greater than. But this because you're talking about the mean in this case, the difference would be we have to put, in this case, you have to P of X bar. Okay. The reason why I put an X bar, because this is about a group. Okay. Like this one is about an individual. This is individual. Okay. So that's two different things. This is two different things. I'm going to show you an example right now. I said, for example, for the first example, I can say if a, oh, I put IA. Let me just give you, what is my pen's eraser? For this one, I can say, for example, if a person I can listen, if a woman, let's put if a woman, let's put a woman, just to be sure. If a woman, that's a O, sorry, I'm just lazy to write them again. Okay, I'll change it. Let's just fix it again. This year is this semester is the only semester I use PowerPoint. I usually use Note. What's the name of that thing again? Notepad, OneNote to do teaching. But this one I want to use PowerPoint this semester. So if a woman, WOMAN, okay, is selected. As you can see, it's as if a woman is selected, what is the probability that something? Okay, as you can see, as if a woman, so I'm going to put P of X. For the other one, I'm going to say if, for example, N, or like can be like 2 women, 3 women, 5 women, 4 women, etc., or 30 women. Let's use the minimum. It's the minimum. Let's put if 25 women are selected, something like that. As you can see the difference between the first one and the last one. One is a group of people, and the other one is just an individual. Okay, but nevertheless, the problem is that StatCrunch won't be able to make difference, but only us know. Whenever I do the paper, we know that this is have to be different. Okay, so remember that one is for a group and the other one is just for individual. So we use P of X. But whenever you do the paper, you have to put with X bar. So whenever you see that term here, P of X bar less than something, I know I put something just about that was a mistake. It can be P of X bar less than or P of X bar greater than, something like that. So if you see X bar in this area, it means that you need to do, this is called central limit theorem. And it's for a group of people, not for a single person. And the formula goes like this in this case, just like you already know about the formula. It's going to be mu and sigma, something like that, okay? But for that one, if I have to do this one, and this is for that guy, this one will be just going to be something like it'll be n, that'll be mu, that'll be sigma over square root of 1, or I can say n, mu, and then sigma. So this is for an individual. The other one is for a group. But the thing is that with the group thing, we want n to be greater or equal than 25, normal, okay? Something like that. Greater than 25 and normal. Or you can say n is less than 25 and normal. That's when it is good. Okay, this is for a group. I normally there was another case I put. What was it again? Okay, I can put it here too. There's a third one. N is greater or equal than 25. You see, 25 is not a good idea whenever it's not normal, but this is, we want it to be large. Okay, not normal. That's the third case. But 25 is kind of sketchy, I mean, scary. Let's put very large, okay? In this case, have to be very large, etc. I think right now is the best time to do one example. I'm not gonna be able at the time to go to start point now, but we can just look at an example just to give you an idea. Okay. Any questions so far? Any questions so far? Did I lose connection?
I do kind of a question. Where am I able to find more practice questions for these problems?
Okay.
Or it's gonna go throughout the slideshow. I was gonna wait until the end of class.
Yeah, that's a good question. I want you to work right now. That's what I want to do. I want you to practice over and over again the practice sheet they give you. I mean, I don't want you to go to, that's why I leave the everything very simple, because I just want, this is statistics. For you to learn is a much other thing. What you can do, just go over that review, that sheet that we have. Go over them over and over again, over and over again, over and over again. Because after I don't know if you probably, if you want to go and math, you're gonna need this all the time. But I was trying to say, I was trying to see if I can keep everything very simple. I know some of you have so many classes. I want to make things like not that heavy, but that's why we see that there's not that much for you. But you're welcome to use the book questions. I think I always put the book for you, right? Or I didn't put the book anymore. Yeah, so use the book to do it. But if not, look, review the notes and then do the practice question for the exam, the one for the exam. I mean, Pearson is good, but not that good. Okay, but practice the review sheet for the exam over and over again, over and over again. And then that's what I will do, because that's why I make the practice sheets available for 30 days. So you can do them over and over again. I thought 30 days this time, but anyway. Then if you keep doing them, then you gotta get used to it. I mean, all of this I'm teaching you right now, if you're not gonna go into mathematics major, I mean, you're not gonna really use that much, but the basic idea that you learn how to make good decisions based on data. That means before I make a decision, I'm gonna make research first. I look at a bunch of numbers, then I make decision. That's the main thing with statistics right now for you. You understand? So it teaches you how to make a good decision before, and also to make you aware of what's going on the road. That's mean if I have a nice product, I cannot just say it's going to be 100% good for everybody, and if everybody start dying, then I get sued. So statistics it help you to get that idea that everything is not going to be 100%. I'm going to put my product on the road, but I need to say that there's small error. So that's what we're doing now. That's what I've been doing for the entire semester, in fact. But unfortunately, we have to use numbers to make you understand all of these things. Okay, so let's keep it simple. But if you want to do more examples, you're welcome to use the example that they give in the book that I also put for you. Hopefully, I think I did put the book for you. Okay, and also if the book doesn't show up in the Canvas, please let me know. Okay, usually I put the chapter that we're working on. Okay, any other questions?
No, sir, that was my main question.
Yes. Okay, no questions. So let's do a quick example. I won't have time again to probably go on second here. This is what happened. This one say the distribution of women's purse rates is skewed right with mu 74. Now they give you a square, but based on the little thing that I just told you, this is going to be asking to be normal distribution. Okay. 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 So the mean is 74 and sigma is 13 a bit per minute. Notice that I'm not able to find the pulse of all the women. They give it to me, so I didn't calculate it. So therefore, it has to be the mean mu and the sigma. Okay, I didn't calculate those numbers. I'm not able to calculate them either. If I find a small sample, but I'm not gonna do that right now. This is what happened. This is what I'm gonna be doing myself. I'm gonna choose 30 women, and I would like to know the probability for them to have a pulse rate less than 72. Okay, on average, you see, this is 30 women. On average, this is on average. Average. Let's put the term average. On average, their pulse to be less than 72 beats per minute. Okay, this is an average value. Okay, just like we're talking about some people going in an elevator. A group of people want to know what's the average of their weight. What's the average of their weight? So I know you understand the idea of average. It's not one person, but it's a group of person. Okay, this is an average. That's mean they take all of them, the thing, and they add them together. You want them, what is probability for them to be less than 72? Okay, first of all, let's understand what we have. Here, this is the mean mu. This is mu. I'm gonna call this one mu x bar right now. And then this is sigma x bar. As you can see, in general, the standard deviation is 13 beats per minute. But for our group of people, which is 30 women, we have that. Mu x bar, and then sigma x bar is gonna be 2.1. As you can see, I have a small data. I have a big, I mean, I have a large sample, and the standard deviation is small compared to the previous one, which was 13 from 13, went from 13 to 2.1, because I have a large sample. The larger your sample size, the smaller the standard deviation will be. It gets smaller. The larger sample size, the smaller will be. That's mean I'm going to be very accurate. So my study will be very fine. So what is the probability for a group of 30 women to have the average purse to be less than 72 beats per minute? That's mean I'm going to take everybody. So understand the idea of average again, just one quickly. It's like I'm taking my entire classroom. I'm trying to see what is the average grade for the class. Suppose the average grade for the class is 72. That's mean everybody together on average are 72. Or I can say what is the average for the entire class to be less than 72. That's the idea behind that. Okay. So that's not an individual person, but this is on average, everybody together. Okay. So if the average of a classroom is 25%, that means there's a problem. You understand? If the average of a classroom is 17%, something like that. But now we want to know what is the average to be less than 72? Is it normal? Okay. So let's see. When I use a stat quench, which I'm not gonna do with you right now, this is what I got. So I put means for 74 for mean. So derivation is 2. As you can see, this one still say X that was said earlier. Giving one. Okay, so as you can see here, a stat quench we're still gonna be say X, but we know we need to put X bar. Okay. See, we put X bar on paper. This is because this is for a group of people. This is for a group of people. Okay. SACON doesn't know that we're doing that for a group of people, but we do. Okay. So whenever you did it, you got 17%. So the probability to have a group of women to have purse less than 72 will be 17%. Okay. So that's mean that is very small. That's mean most people, most women will not have a purse less than 72. That's what it means. That's mean about 80% of the women will have a purse more than 72. That's what it means. 70% of the people, or 83, we can say 83, yes. 83% of the women will have a purse more than 72. I mean, having a purse less than 70, it's on 72 is about 17% of the population. Kind of like not really, it can happen, but not that often. Okay. If the number that was big, then that'd be a problem. That's when if all women, if the probability was less than more than even about 20 or even 80%, that's when these people probably are very sick. But a wealthy woman, a wealthy people, you know, kind of weird. It has to be 17%, something like that. Okay. So okay, so that was the question I want to put to. So energy is the definition right here. Let's see. This is how they just say. You say if one woman, this is for one person. If you say one person, then you have to put P of X. Okay, and at the same time, if it's skewed to the right, it's not normal. Okay, but that's why I say don't worry about the skew to the left to that, but you have to do what you're supposed to be doing. So the formula will be different, and the formula will be different. Okay. All right then. Quickly thing I need to explain to you. Let's see how many minutes I have left. I have 10 minutes left. So I'm gonna wash up quickly on this thing. Population sample. Okay, again, this is for one person. We'll talk about that before. I'm gonna skip it. But as you can see, this one is not normal because you have a group of people, then you're gonna have to use for one person. I'm not using that example too much, but if it's just for one person, this is what you do. But because here earlier it was skewed, it's not normal. It has to be normal. But because you have a huge, earlier we have a huge sample, a large sample, even though it's not normal, we still can work it out. That's what we talked about before. What did I talk about again? Okay, if it's not normal, and then the sample is large, it's okay. It's okay. We said that before. It's okay. All right. But compare the other one. For this one, it has to be normal all the time. Okay. And this is one that the thing that I wanted to just remember, just become ending. Right here. What is it again? This little thing right here. Whether in this one right here, population skewed to the left. Then you have to be semi distribution symmetric. So you're gonna assume this is normal for last semi distribution. Okay. Let's see. I don't think I'm supposed to put mute here, but that's fine. Okay, so let's talk about more stuff. So this one, I'm gonna let you read those little thing on this side. Okay, so for you to read, so this for you to read, we talked about them before. Okay, this is population distribution. This one is sample. So individual and group. We talked about that before. Our surveys, etc. So just read it. So the last thing we talk about is something called the t-distribution. So here we're gonna be able to make the difference whenever you have to do it. And this is the case, and I mean, we're gonna tell you that start points can make the difference. Sometimes your standard deviation is not given to you. You don't know what to find for the standard deviation. So therefore, if you don't know the sigma, we're gonna find the z-score. So you're gonna have to do the sample standard deviation. Okay, the sample standard deviation will be given to you because sigma is unknown. Okay, so this is a formula for the t-distribution, kind of the same thing. As you can see, if you can remember for the z, it goes like this as well. X bar minus mu over sigma over square root of n. Okay. I can say for this one, that would be mu, and then sigma over square root of n. And then this guy here will be just going to be mu. And so I put the sigma, I'm going to put s over square root of n. Because sigma is unknown. So start quants or even tier 83 can make the difference for you. There should be a thing that you can click and say sigma is unknown. So this is what we do. Okay. Again, this is a formula again that this is not error. And everything kind of the same thing. Now we do the same thing, and then kind of the same idea. We're gonna have bear shapes. So these are things probably gonna use in your notes for bear shape, pairs, and a little bigger than normal. Okay, given n, there's the n minus 1 degree of freedom. So if you have n and there's something called degree of freedom, suppose they ask a question. Given that a sample of n is equal to 8 or 9, suppose n is equal to 9. What is the degree of freedom? In this case, the degree of freedom will be 8. It has to be the degree of freedom. It's going to be n minus 1. These are definitions I need to remember. That's going to be 8. Okay. For large degree of freedom, the distribution is almost normal. If you have a large degree of freedom, the distribution is almost normal. okay? If it's very large. So that'll be a time Z until kind of the same thing, okay? So everything will be kind of the same thing. The only thing we're gonna have to do whenever you're using the TI-84, we're gonna specify that the sigma is unknown. Or if you did the side crunch, you're gonna calculate in that the sigma is unknown, and that should work the trick for you. Okay. I'm gonna have to stop here. And then what I'll do to help you out, a little bit, what I'm gonna be doing, just to, I don't want to waste too much time, I'll upload the notes for today. I'm gonna upload the notes, and then on Thursday, I'll upload them again, but with the next part I'm gonna be doing, okay? I'm gonna upload everything for all chapter 9 with you, and even I'm gonna be saying I'm gonna upload it for you. Probably if you wanna do a further reading, you can go over it. Then I'm gonna update. I'm gonna upload an update version on Thursday, okay? So I'm gonna stop here, and then if you have any question, please, you're welcome to say and ask me question.